Hello, myself Yamuna. Welcome to Yamuna's physics classes. Today we have to discuss the topic toroid, that is section 4.8. Now last video we have detailed discussion on solenoid. So once you know the idea solenoid, it is very easy for you to learn toroid. And we need to find out what's the magnetic field of the toroid. You can easily find that it is same as B equal to mu 0 Ni, same value as that of a solenoid, with a very little bit of difference for the value N. You know, N is the number of turns per unit length. So here again it is the same but with a slight modification. Okay, so let us start. What is a toroid? Toroid is a hollow circular ring on which a large number of insulated wires or turns are closely wound. It is otherwise known as endless solenoid. Means I told you solenoid is nothing but a spring. If you have the spring and if you hold the two ends of the spring together, it comes out to be endless spring or a helix. So that is known as toroid. So this is somewhat a picture of solenoid which shows that the two ends are brought together. The two ends of the helix or the spring are put close together to form a toroid. So in this figure, the inside it is mentioned that hollow circular ring. So this is a circular ring which is hollow or empty. You can space something well inside as the core, but here we have placed the green shaded portion is simply hollow. That space is hollow, that shows the space within the solenoid which is hollow or air cored solenoid. Toroid. Now when you imagine about a solenoid or toroid, definitely in our mind there should be two terms: the current, the magnetic field. Moreover, the lesson itself says magnetic effects of electric current. So for sure we have to register two words. One is current and the magnetic field. So we'll discuss the figure a little bit in detail. We have done in the solenoid, but still once more. Okay, so look at the figure. You can see current is entering through this point. It is entering through the point. Goes like this. Here again comes out, enters, comes out, enters, comes out, enters. Likewise it comes and finally comes out through this wire. So you can see at some points I have drawn the cross. All these cross represents here the current is entering, 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 entering. At 8 points you can see the current is entering the loop, and at the same time 8 points it is coming out of the circular, what you call the hollow circular ring. So this hollow circular ring has 8 points where it is getting into, and at the same time 8 points where it is coming out. So these points are to be registered in mind. So well inside the toroid, some points where current enters, outside the circular ring where current is coming out. Okay, now so that's about the directions of the current. Now about the magnetic field, here you are going to apply right hand thumb rule. Right hand thumb rule is there for circular loop as well as straight conductor. Here it is circular loop. So I have to take my fingers, right hand fingers, curl them in the direction of the current. So let me take it in that direction of the current. So this, I put the fingers in this direction, take it outside in this direction. Look at this. So what is going to happen? Here my current is coming out and entered. This is the direction out, shows magenta. This is coming out and inside. You can see it is well inside into, that is given by orange. So my direction of the thumb, you can see the direction of thumb is axially. It is going axially in this direction. Clockwise direction it is going axially. Wherever I cast it will be the same. So the axis, along the axis, the magnetic field is in the clockwise direction. So this yellow turns shows insulated copper wire. The white circle shows direction of the magnetic field. Hope the three things are clear. One, the cross mark with orange, magenta with dots, white circle with the direction of the magnetic field. Okay. Now, like the solenoid itself, we have to show that, well, inside you don't have any magnetic field, well, outside you don't have any magnetic field, and the magnetic field is residing only inside this core or circular ring. So, magnetic field B of a toroid is directed along its circular axis and constant in magnitude. The magnitude will be the same. The value is mu 0 Ni. So, we are going to prove the same thing, exactly the same thing as a solenoid for a toroid. So, we have to prove this. For proving the same thing, we are using Ampere's circuital law. With the help of Ampere's circuital law, we are going to prove in and out zero magnetic field, well, inside you have magnetic field. So for that, the same figure is taken in a cross-sectional view. The whole toroid I have cut parallel to the plane of the board. Same as cutting solenoid, we cut this parallel to the plane of the board. So in solenoid, we had a straight wire like this or a straight cylindrical cross section, but this we have a circular cross section just because this is a circular loop or a ring. Clear? Now the same things redrawn. Orange cross inside, magenta dots outside. Inside this is the core. The shaded portion, greenish shaded portion is the core, and the circle, the second named second is the second loop as well as the direction of the magnetic field. So here in this figure, the 2 shows the second loop and the direction of the magnetic field. So we construct 3 Amperean loop for the purpose. 1 well inside, 2 inside the core, 3rd one outside. Now look at each one separately. So for the first loop, loop number 1, which radius R1. So the loop number 1 having a radius R1. It is crystal clear, inside that loop you don't have any wire. No wire inside the loop. So no current, no magnetic field. So apply Amperean circuital law, what you will get? The Amperean loop encloses no wire, so no current, so no magnetic field. So for the loop 1, Ampere's circuital law gives B1 to 0. No current, no magnetic field. Clear? Now coming to the third one, we will come to 2 later on. Third loop, it is very clear. You can see that how many dots are there, same will be the number of cross. If you could check 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So how many dots are there? Same number of cross are there. Because why? Same number of wire is going in and coming out. So the current going in will be same as current coming out. So what will be the number of dots? Same as number of cross. Means total current will be 0. Same as the case of solenoid. Solenoid, you know, at the outer portion, what is happening? Magnetic fields are going into, at the same point, the magnetic field is coming out. So the net value goes to 0. Here again, B3 goes to 0. Now finally come to the point 2, loop 2. What about loop 2? This is the loop 2, second loop. This is the second loop. In the second loop, what is the condition? Only cross is seen. You look at the loop 2. Well, inside the loop 2, you can see only cross. Nothing else, only cross. This dot is outside the loop 2, need not consider. So inside you have only this cross. So you have to find the net current. We need the right hand side. What is the right hand side? Whatever is the right hand side, it is mu 0 sigma I. What is sigma I? Sigma I means it is defined as number of turns into current in each turn. So each turn carries a current I. But how many turns are there? How many turns are there? How many turns means this loop 2 has a length 2 pi r2. Just if you place that 2 pi r circumference straight away, that is a length 2 pi r2. 2 pi r2 is the total length, but the unit number of turns per unit length is small n. So how to get the total number of turns? 2 pi r2 into small n. Usually we do. Small n is defined as capital N by L, you know. So here it is r2. Therefore, what is total number of turns? Small n into 2 pi r2, because we are considering the second loop here. So that is the total number of turns into I. Total number of turns into I. That is sigma I. Now what about the left hand side? For left hand side, I told you this is loop 2 as well as the direction of B. So loop 2 is taken in such a manner that the direction of B and the direction of DL are the same. Therefore, theta comes to 0. B dot DL is B DL cos theta, cos 0 1. So LHS becomes B into integral DL. What is integral DL? Length of the second loop. Length of the second loop is definitely 2 pi r2. So 2 pi r2 and 2 pi r2 cancels. The remaining is B equal to mu 0 times Ni. Clear? Now here N, you has to be careful. Small n is the number of turns per unit length itself, sure, but you are not taking R2. You are taking R as the average of R1 and R2 by 2. You know that you don't have loop 1, you need not take loop 3, you are considering only loop 2. So, but you should not take 2 pi r2. Instead, you should take r as r1 plus r2 by 2. What is r1? Inner radius. What is r2? The radius along the axis. And you have to consider the radius as r as the average of r1 and r2. That is r1 plus r2 by 2. That's the only difference between solenoid and toroid when you find the value of magnetic field. Hope it is clear. If you have any doubts, you can comment, and in the playlist in the description I will be giving the channel link, so you can go and see any previous videos, for example solenoid or through an axis of a circular coil. All these things are required when you come to learn solenoid and toroid. Moreover, Ampere circuit law is also for sure required. So thank you for listening.